On July 31st, at a depth of 6 kilometers below sea level, something happened underneath Mount Pelean that shouldn't have happened. One earthquake, out of 124 that week, came from a place none of the others did. And it's the reason volcanologists are now watching this mountain every single day. Let's start with the numbers, because the numbers are what triggered all of this. Between July 24th and July 31st of this year, the Martinique Volcanological and Seismological Observatory recorded 124 volcanic earthquakes underneath Mount Pelean. The week before that, they recorded 45. That's almost 3 times as many earthquakes in 7 days. Across the entire month of July, the total climbed to 331 volcanic earthquakes, averaging around 85 per week. On paper, that sounds like a mountain waking up in a hurry. And in a way, it is stirring. But the story is more complicated than a simple spike on a graph, and if you actually look at where these earthquakes came from, you'll understand why scientists are being so careful with their words right now. Almost all of these 124 earthquakes were shallow. We're talking about depths between roughly 0, 7 and 1, 7 kilometers below the summit. None of them exceeded a magnitude of 1. Nobody on the island felt a single one. In volcanic terms, this kind of shallow, low-magnitude seismicity is often linked to something far less dramatic than magma on the move. It's usually tied to a hydrothermal system, a network of superheated water and steam trapped and shifting beneath the surface. Mount Pelean has had this kind of restless hydrothermal activity going on since 2019. That's 7 years of a mountain that occasionally rumbles, occasionally vents a bit more gas, occasionally logs a cluster of tiny quakes, and then goes quiet again. For 7 years, this pattern has meant essentially nothing in terms of eruption risk. If July had ended there, this wouldn't be a story at all, but it didn't end there. Buried inside that batch of 124 earthquakes was one that didn't fit the pattern. One earthquake was located at a depth of 4, 6 kilometers below sea level, slightly west of the lava domes that sit at the summit. That's roughly 3 miles down. Every other earthquake that week stayed within a mile or so of the surface. This one dropped far deeper, into territory that matters a great deal more to volcanologists, because that depth range sits right in the corridor between the shallow hydrothermal system above and the magma reservoir believed to exist further below. It's the connective tissue between water and molten rock. When an earthquake shows up down there, scientists pay attention, not because it proves anything on its own, but because it's the kind of signal that, if it starts repeating, could mean fluids or gases are beginning to migrate between the magma system and the surface layers above it. To be absolutely clear, one earthquake at that depth does not mean an eruption is coming. Volcanologists will tell you the same thing again and again. Single data points are not patterns, and patterns are not certainties. But it's also not nothing. It's the kind of thing that shifts a monitoring team from routine observation into a slightly higher gear of attention, because it's the type of signal that has, historically, at other volcanoes around the world, sometimes preceded periods of increased unrest. The honest answer, and the one the observatory itself gives, is that they don't yet know what this particular earthquake means. They need more time and more data before they can say anything with confidence. That uncertainty is exactly why this story is worth understanding properly, instead of either panicking over it or dismissing it outright. So let's slow down and build the full picture, starting with why Mount Pelean, of all volcanoes, gets this kind of attention in the first place. Mount Pelean sits on the island of Martinique, a French Caribbean territory located roughly 1,500 miles southeast of Florida. It's a stratovolcano, the classic cone-shaped type built up over thousands of years by layers of hardened lava, ash, and volcanic rock. Geologically, it exists because of subduction, the process where one of Earth's tectonic plates is forced beneath another, generating the heat and pressure that feeds volcanic systems all along this arc of islands in the Lesser Antilles. Pelean isn't some obscure minor volcano. It has a name that carries real historical weight in volcanology, and that weight comes from a single event in 1902. On the morning of May 8, 1902, Mount Pelean erupted with a specific and particularly lethal kind of violence. It didn't simply explode upward. Instead, it released what's known as a nuée ardente, a French term meaning glowing cloud. This is a fast-moving current of superheated gas, ash, and volcanic debris that hugs the ground and races downhill at speeds that can exceed 100 miles an hour, with internal temperatures hot enough to instantly ignite or incinerate almost anything in its path. On that morning, this glowing cloud swept directly into the town of Saint-Pierre, which at the time was the cultural and economic capital of Martinique, a thriving port city home to tens of thousands of people. The destruction was almost incomprehensible in its speed. Saint-Pierre wasn't gradually damaged or slowly evacuated. It was erased in a matter of minutes. Estimates place the death toll at around 30,000 people, and the eruption is still considered the deadliest volcanic disaster of the 20th century. To put that number in perspective, in less time than it takes to boil a kettle of water. An entire city's worth of people lost their lives. Out of a population in the tens of thousands, only 3 people are known to have survived within the town itself. Their stories are almost eerie in what they reveal about the nature of that glowing cloud. One survivor, a man being held in a partially underground jail cell with thick stone walls and minimal ventilation, was shielded enough by that structure to survive, though severely burned. Another survivor lived at the very edge of the city, on the margins of where the cloud's full force was felt, and escaped with serious burns of his own. A young girl survived by fleeing to a sea cave, using the rock itself as a barrier against the heat and debris moving through the town. What ties these 3 stories together is telling. It didn't matter whether you were indoors or outdoors, upstairs or downstairs, in a stone building or a wooden one. The only real protection that day was solid rock standing directly between a person and the mountain. That's how total the destruction was. And it's why the 1902 eruption still anchors every conversation about Pele more than a century later. After 1902, the volcano had one more eruptive period, between 1929 and 1932, which was far less deadly, in part because authorities had learned brutal lessons from the earlier disaster and organized evacuations in time. Since 1932, Mount Pele has not erupted. Decades of relative quiet followed. But relative quiet doesn't mean dormant in the way people sometimes imagine, with nothing happening beneath the surface at all. Volcanoes like Pele are considered active and monitored continuously, because dormant periods of many decades are common between eruptions, and because the underlying magmatic system doesn't simply switch off. That brings us to 2019, which is really the starting point for the current chapter of Pele's story. Beginning that year, the Martinique Observatory noted an increase in seismicity beneath the volcano. This wasn't a sudden crisis. It was a gradual uptick, slow return of tremors and small quakes after a long period of relative calm. By December of 2020, that increase in activity was significant enough that authorities raised the volcano's alert level from green, meaning normal, to yellow, meaning vigilance. Yellow is the second tier on a 4-color alert scale, and it essentially tells both scientists and the public that the volcano is showing signs of unrest worth monitoring closely, without indicating any immediate danger. That yellow alert level has remained in place ever since, through 2021, through 2022, through every year up to now. In other words, Mount Pele has technically been in a state of elevated vigilance for roughly 6 years already. This is a crucial piece of context, because a lot of the recent headlines about Pele make it sound like the mountain just woke up out of nowhere this summer. It didn't. It's been rumbling, quietly and inconsistently for years, and during those years the numbers have swung considerably. This isn't the first time weekly earthquake counts at Pele have spiked. Earlier in 2026 itself, before this July surge ever happened, one single week in late April saw the observatory log 494 volcanic earthquakes, a number significantly higher than the 124 recorded in the last week of July that's making headlines now. So when you hear that earthquakes tripled in a week, that's accurate, and it's worth paying attention to, but it's also worth knowing that this volcano has produced even larger weekly totals earlier this same year without anything resembling an eruption following. Context like this doesn't make the current situation meaningless. It just means the raw earthquake count alone isn't the most reliable signal to fixate on. What actually matters more is a combination of factors, and that's where the second thread of this story comes in: ground deformation. Since May of 2026, instruments around the summit of Mount Pele have been detecting measurable ground movement. Using permanent GPS stations positioned around the upper slopes, scientists have tracked the distance between fixed points slowly increasing centimeter by centimeter. This is what volcanologists call inflation, and it happens when pressure builds beneath a volcano, physically pushing the surrounding rock outward and upward, the way pressure inside a balloon stretches its skin before it either stabilizes or bursts. Over roughly 6 months leading into July, that inflation added up to somewhere around 3 to 4 centimeters of cumulative ground displacement. In the most recent 4-week stretch tracked by the observatory, the rate of that movement was measured at approximately 2 centimeters per month, and notably that rate had slightly declined compared to the month before it. This is where things get genuinely interesting, because you now have 2 different monitoring signals telling 2 somewhat different stories at the same time. On one hand, seismic activity, the raw number of earthquakes, spiked dramatically in the final week of July, tripling from the week before. That points toward increasing unrest. On the other hand, the ground deformation, the physical swelling of the volcano, actually slowed down slightly over that same recent period. That points toward decreasing pressure, or at least a pause in the rate of pressure buildup. Scientists at the Observatory have described this slowdown in deformation as a positive sign, but they've also been careful to say that several more weeks of continued observation are needed before anyone can say with confidence whether the underlying pressure is genuinely easing, or whether this is simply a temporary lull inside a longer, ongoing process. Nobody currently knows for certain which of these two signals will end up being the more important one, and that honest uncertainty is really the core of the situation right now. So where does the deep 6-kilometer earthquake fit into all of this? It's essentially the wild card, the one data point that doesn't cleanly belong to either the shallow hydrothermal seismicity or the summit deformation pattern. It sits in that connective zone between the water and steam system closer to the surface and the deeper magma reservoir believed to exist further underground. An earthquake at that depth can occur when hot fluids or gases begin migrating between those two zones, essentially probing or fracturing rock along a pathway that could, in theory, eventually allow material to move closer to the surface. One such earthquake is not proof that this migration is actively happening. It could be an isolated event with no larger significance at all, similar to countless other individual anomalies volcanoes produce over the years without consequence. But it's also exactly the kind of signal that observatories watch for, specifically because if it starts to repeat, or if more earthquakes begin appearing at similar depths in the following weeks, it would represent a meaningful shift in the character of the unrest, moving from purely shallow hydrothermal activity towards something involving the deeper magmatic system. It's worth being very precise here about what has and hasn't been said officially, because this is the kind of story that tends to get exaggerated as it spreads. The Martinique Observatory has not issued any warning of an imminent eruption. There is no evacuation order. There is no emergency declaration. The alert level remains at yellow, the vigilance tier, exactly where it has sat since December of 2020. In their own written assessment, the observatory stated plainly that the probability of eruptive activity in the short term remains low. At the same time, they added an important qualifier, noting that given everything observed over recent months and years, an evolution of the situation in the medium term, meaning a time frame of weeks to months rather than days, cannot be ruled out. That's a carefully balanced statement. It's not an alarm, and it's not a dismissal either. It's scientists telling you as accurately as they can that they genuinely don't know yet what comes next, and that they're watching closely enough to catch it if the pattern changes. Why does any of this matter beyond Martinique itself? Partly because of what's at stake locally. The town that once stood as Saint-Pierre was never fully rebuilt to its former scale after 1902. Its population today is a small fraction of what it was at the time of the eruption. But Martinique as a whole is home to hundreds of thousands of people, with communities and infrastructure spread across the northern part of the island, well within range of any future pyroclastic activity should the volcano ever reach that stage again. There's also a broader regional dimension. Martinique sits along air corridors that connect the Caribbean to North America, and a significant eruption producing ash clouds could disrupt flights across the region, similar to how ash from volcanic eruptions elsewhere in the world has grounded aircraft and rerouted air traffic in the past. None of this is meant to suggest that disruption is coming. It's meant to explain why a volcano most people outside the Caribbean have never heard of suddenly showed up in international headlines over the past week. It's also worth taking a moment to appreciate just how sophisticated the monitoring around Pelean actually is, because that infrastructure is precisely why we know as much as we do right now. The observatory tracking this volcano operates continuously, running a dense network of seismometers that detect and locate even the smallest tremors, combined with GPS stations sensitive enough to register ground movement measured in millimeters. This isn't guesswork or speculation. It's a scientific institution with decades of data on this specific volcano, comparing current readings against historical patterns, going back through past swarms in the 1980s, in 2007, and in 2014, along with the more recent unrest beginning in 2019. That long historical baseline is exactly why scientists can say with some confidence that a single deep earthquake on its own isn't unprecedented or automatically alarming, while also explaining why they're not simply shrugging it off either. They have enough historical context to know what normal noise looks like at this volcano, and enough respect for its history to take any deviation from that noise seriously. So what actually happens next? Realistically, the answer is more monitoring, more weekly reports, and more waiting for patterns to either strengthen or fade. If the deep seismicity at that 6-kilometer depth repeats in the coming weeks, that would be a significant escalation worth close attention, potentially indicating that fluids or gases really are migrating upward from deeper in the system. If ground deformation continues to slow and eventually stabilizes entirely, that would support the more reassuring interpretation, suggesting the pressure buildup since May is leveling off rather than accelerating towards some kind of critical point. If, on the other hand, both seismicity and deformation begin trending upward together in the coming weeks, that combination would represent a much stronger signal of genuine escalating unrest, the kind of pattern that has, at other volcanoes historically, sometimes preceded a shift toward eruptive activity. Right now, none of those clearer patterns has fully emerged. What exists is a mixed picture. One signal up, one signal down, and one anomalous data point that doesn't fit neatly into either category. This is in many ways the reality of living alongside an active volcano. It's rarely a single dramatic moment that announces itself clearly in advance. It's usually a slow accumulation of small, ambiguous signals, evaluated patiently over weeks and months by people whose entire job is interpreting exactly this kind of uncertainty. The people at the Martinique Observatory aren't being cautious out of excessive politeness or bureaucratic hedging. They're being cautious because volcanic systems genuinely are this uncertain, and because the history of volcanology is full of both false alarms that never developed into anything, and quiet periods that, in hindsight, turned out to be the calm before something much larger. Getting that balance right, communicating real risk without either downplaying it or exaggerating it, is exactly the difficult job these scientists are doing in real time right now with Mount Pelean. For anyone following this story going forward, the numbers to actually watch aren't necessarily the total weekly earthquake count on its own. As we've already seen, that number has swung wildly throughout 2026, and a high count by itself hasn't meant much in the past. The more meaningful things to track are whether additional earthquakes appear at that deeper range near the domes, whether the rate of ground deformation starts climbing again after its recent slowdown, and whether the observatory's own language shifts in future weekly and monthly reports. Right now, their assessment remains calm and measured. If that tone starts to change, if the wording shifts from watching closely to actively preparing, that would be the real signal worth paying attention to, far more than any single week's earthquake tally. It also helps to understand why a nuée ardente is so uniquely dangerous compared to other kinds of volcanic activity, because that's really the reason Pelean occupies such a specific place in the history of volcanology. Many eruptions people picture involve lava flowing slowly downhill, something a person could walk away from without much difficulty. A nuée ardente is nothing like that. It forms when a volcanic dome, a mass of thick, viscous magma that is piled up near the summit, either collapses under its own weight or is shattered by an internal explosion. The result is a mixture of superheated gas, ash, and rock fragments that doesn't rise gently into the sky the way an ash plume does. Instead, because it's denser than the surrounding air, it hugs the terrain and rushes downhill under gravity, accelerating as it goes, sometimes reaching speeds well over 100 miles an hour with internal temperatures capable of exceeding several hundred degrees Celsius. There is essentially no outrunning something like that on foot, and in 1902, there was almost no warning either. This eruptive style is now formally referred to in volcanology as a Pelean eruption, named directly after this mountain, because Mount Pelean became the defining case study scientists used to understand and classify this exact type of catastrophic volcanic behavior. Every time a volcanologist anywhere in the world discusses a Pelean-style eruption, they are, in effect, referencing what happened on this island in 1902. That historical weight is part of why modern monitoring here is taken so seriously, and why even a small, ambiguous shift in the data gets attention that a similar shift at a lesser-known volcano might not receive. The 1902 disaster fundamentally changed how volcanic hazards were studied and communicated to the public. Prior to that eruption, warning signs, including increased fumarole activity, minor ash emissions, and small earthquakes in the weeks beforehand, were observed but not acted on with the urgency that hindsight now shows was necessary. Evacuation was delayed, in part because of political pressure tied to an upcoming election, and by the time authorities recognized the true scale of the danger, it was already too late for the vast majority of St. Pierre's residents. That failure became one of the founding lessons of modern volcanic risk management. That ambiguous warning signs should be taken seriously and communicated honestly, rather than downplayed for convenience. It's not an exaggeration to say that the entire discipline of monitoring dormant volcanoes for early warning signs owes a significant debt to what was learned, tragically, from Pelean's failure to be taken seriously in early 1902. That lesson is visible in exactly how today's observatory communicates. Instead of staying silent or waiting for a crisis to become undeniable, they published detailed weekly reports, openly listing raw earthquake counts, depths, magnitudes, and deformation rates for anyone to review. They explicitly state both what they know and what remains uncertain, rather than offering false reassurance or manufactured alarm. This kind of transparent, continuously updated reporting is a direct product of the historical lessons this exact mountain taught the scientific community more than a century ago. In a strange way, Mount Pelean's greatest tragedy reshaped how volcanoes are watched worldwide, and that legacy is quietly present in every weekly bulletin the observatory publishes today, including the one describing this July's unusual deep earthquake. It's also worth remembering that Martinique isn't monitored in isolation. The island sits within the Lesser Antilles volcanic arc, a chain of islands stretching from Grenada in the south up through Martinique, Dominica, Guadeloupe, Montserrat, and beyond, all shaped by the same subduction process beneath the Caribbean plate. Montserrat, further north, experienced its own devastating eruption in the 1990s, when its Soufriere Hills volcano became active after centuries of dormancy and eventually destroyed much of the island's capital. That eruption is often cited by scientists studying Pelean as a reminder that long dormant volcanoes in this exact region are fully capable of reactivating with serious consequences, even after generations of apparent calm. It's part of the reason regional monitoring agencies coordinate closely, sharing data and expertise across island observatories, because the geological forces driving unrest at one volcano in this chain often reflect broader patterns playing out across the entire arc. None of this is meant to suggest that Mount Pelean is following the same path Soufriere Hills did, or that an eruption is somehow more likely because of what happened on a neighboring island decades ago. Every volcanic system behaves differently, shaped by its own unique magma chemistry, structural history, and pressure conditions. But it does help explain the broader mindset behind why this region takes even modest anomalies seriously. The Caribbean has learned more than once that dormancy lasting decades is not the same thing as permanent safety, and that the transition from quiet unrest to active crisis can sometimes unfold faster than anyone initially expects. For now, Mount Pelean sits exactly where it has sat for years, at yellow alert, under close watch, quietly restless, in the way it's been restless on and off since 2019. One earthquake at 4. 6 kilometers depth doesn't rewrite that story on its own. But it's a reminder that beneath a mountain with this particular history, even a single anomalous signal is enough to make an entire observatory sit up and pay closer attention week after week until the picture becomes clear one way or the other. And when it does, whichever direction it goes, you can be sure the data will be there, quietly building toward whatever comes next.